In this lecture, we're going to look at taking higher order derivatives, and I like to frame the discussion around the Taylor series. Otherwise, I just think it's just taking derivatives for derivative's sake. Okay, so again, here's the Taylor series theorem. So the idea is I'm going to represent the function, any function that's differentiable. So when I say d infinity, I mean it has all derivatives of any order I want to take. And then I can represent it as a, polynomial that goes out to infinity. In practice, of course, you'll just truncate it at some point and accept some little bit of error, and we'll look at that in the examples we do. So again, essentially what I'm doing is I'm just taking the derivatives, higher order derivatives, and evaluating them at a point. So it's a generalization, if you will, of the linear approximation of the tangent line. So here's our first example. So let's go straight forward. Here's just a simple function, and we want to find the third Taylor polynomial. About this point, x equals 1. When I say point, again, it's a function, so if I say x equals 1, there's an xy ordered pair value. It's a third derivative, right? I just really want to take the third derivative. So again, let's just set it up. The first derivative we've been doing, it's exactly the same as we've been doing. It's the same problem. I know since the function's differentiable, I can apply the differential operator, and then I can evaluate the derivative function when x is 1. Okay, so I'm going to define the function, again, a preliminary step. And I just want to make sure it's all in the correct format. What the domain, I see I only gave you the rule, so your job is to figure out the domain. I'm just going to push a little algebra here. Again, I know nobody likes to do it, but you don't get better when you don't do it. When you write x to the 3/2, and again, I have all this listed on that crib sheet that I attached, it means one of two things, right? I can write it either way. X to the 3/2 means x to the 1/2, right? So the square root of x cubed. Or it means x cubed to the 1/2 power, or the square root of x cubed. Either way, maybe the first one you can see that, so I'm just writing it up here. Either way, you can see that, in fact, x has to be non-negative, right? If I'm dealing with real numbers, I want x to be non-negative. And, okay, so that's the idea. So, again, we're just going to take the derivative based on the original rule, 4 to the x to the 3/2, right? A constant times x to the power. But this helps you understand what the domain is. It wasn't given in the statement of the problem, right? I gave you only the rule, and your job, you have to figure out what the domain of definition is. And again, this will play out when you actually find out where the Taylor series is applicable and so forth and so on the domain. You'll learn more about that. I'll play more of that next semester. But again, I don't want to just ignore the algebra. You don't get stronger if you just ignore it. Okay, but for us at this point, just take the derivative, right? We're just going through practicing really higher order derivatives and trying to appreciate what the Taylor polynomial means. So again, if you haven't done it, just try it. This is just practice what we did in the last lecture. It should be a formal process. You shouldn't have to take more than, 30 seconds doing this. So if you haven't done it, give it a shot. Just go. Okay, I'm going to start off again in the same way I always do. Substitute in the rule. You look at this, the only possibility is to take out the constant. What's left, you only have the power rule, and now it's just a matter of cleaning it up. Okay? But since I'm going to take the second derivative, it's not a bad idea to look at the domain of, look at the second derivative as a function, and that's really what I'm doing. Again, for a test, I don't know if I take the time to do this, but really what you have is, if I'm taking the second derivative, I'm taking the derivative of the first derivative. And as a function, this is what I have. Now what I want to point out is the domain here, even though square root of x is defined for all x greater than or equal to 0, this is the derivative function. And we've only taken the derivative in interior points, right? I mean, it's a technicality, but again, I want to explore these ideas with you is why I'm introducing it. Just as we did continuity up into including the walls, right, on closed and bounded intervals, you can define the derivative as one-sided, right? So you could do this and go up to, say, x greater than or equal to 0. We haven't done it. So again, you might want to do it. You might want to know what the derivative itself being continuous up into the wall. When you talk about heat transfer concepts, the gradient of the temperature is the heat transfer. So these issues do play out, for example. But well, I'm leaving that aside. We're not, in terms of this course, I've only defined the derivative in internal points, and that's why I have x greater than or equal to 0. Again, I wouldn't test you on it. I'm not trying to trick you on it. I'm just saying there are mathematical reasons for this. You can explore other ideas as well. Okay, so just be aware of what you're doing and you're not surprised then, okay? Think what you're doing. But my point with this is I'm trying to say that fx is a function. It's derived from the function f. It is a function. So when we take the second derivative, we just repeat exactly the same process, right? We have a preliminary step. We know what the function fx is, right? That would be my step 0. And then, again, it's differentiable on the interval, so I can use the differential operators and so forth. And again, you see, the function fx now goes in. The second derivative function fxx comes out via the differential operator. So when you're taking higher order derivatives, you're just repeating the same problem over and over again, right? It's the same thing. So I substitute the rule. And again, if you haven't done it, just do it. It's, pause a second and go. So I'm going to take the constant out and apply the power rule and do algebra. And again, how you want to represent it is fine. Again, it's whatever. But again, it's a function in its own right. Remember, the function fx went in, the function fx comes out. And again, I'm trying to represent this to show you that, in fact, it is a function. And notice clearly x has to be greater than 0 here because you're dividing by square root of x, right? So you couldn't have x equals 0 here at all. So in the case of fxx, this comes out quite naturally. And if I want the third derivative, right, the second derivative is here. This is your preliminary step. Make sure you know what you're talking about with your function fxx. It's differentiable wherever it's defined. It's fine. So I'll use the differentiation rule. So the third derivative equals, right, comes out when I apply the differential operator to the second derivative. Again, try this. I'll do it now, but again, if you haven't, pause and try it. I'll just substitute in the rule. I'm just going to take the constant out, power rule, clean it up, and that's what I have. Now I have the third derivative. Okay, so this is fairly standard. What I like to do, though, is, like I said, the Taylor series. So we're going to find the third Taylor polynomial. About, again, when I say x equals 1, because it's a function, this specifies a point, right, a point on the graph. I'm just summarizing all our data here. Here's my function f, my first derivative, my second derivative, and my third derivative, right, all listed here just for convenience. And all I'm going to do is I'm just going to make a table. I mean, it's really that simple. Again, on the web, you just type in a Taylor polynomial calculators, or I forget what I typed in, Taylor series calculator, and it comes, you just plug in the function, how many terms you want, and what the a is, and you're good to go. But anyhow, I just list my function rule, the derivative rule, second derivative rule, third derivative rule, as many as you want. And then I'm just going to evaluate each of these around at a is 1. Right? So in this case, f of 1 is 4, and so forth. The derivative at 1 is 6. I mean, it's a very straightforward problem. Again, work smarter, not harder. And the beauty is, I can turn anything into a polynomial if it has derivatives. It's smooth enough. Here's my formula. So I'm saying this function is approximately, that's what the wavy equal sign is, the third Taylor polynomial, and that's defined by this formula. Again, notice, it's about x equals 1, so everything is evaluated at 1, right? So if it's the first derivative, divide by 1, x to the first power, second derivative, 2 times 1, this term squared, third derivative, 3 times 2 times 1 cubed. And I'm just going to plug in the data, right? When it's x equals 1, so it's x minus a, x minus a, x minus a. The function is approximately equal to the third Taylor polynomial. So again, for me, replace the function by the Taylor polynomial. F of 1 is 4, so just plug 4 in there. The derivative is 6, so I'm just going to plug 6 in there. Second derivative is 3, I'm just going to plug 3 in there. The third derivative is minus 3 halves, so plug that in. Now it's just, so if I ask you this on a test, you don't have to simplify, right? Don't bother simplifying. But if you simplify it, and again, it's a bit of work, I really had to work on this, it's just this polynomial. Notice x cubed, constant x cubed, constant x squared, plus minus constant x plus constant. That's just a polynomial, right? I mean, that's the beauty of this. It's just a polynomial. So whether you're going to, we haven't done it yet, but integrate, differentiate, or even just use it, the function is a polynomial. Now, again, you're going to make some error, but again, we'll look at the picture and see. Here's the picture. My function is the red line. And notice the linear approximation. Again, if you're working in a neighborhood of 1, x equals 1 minus 4, this point, the linear approximation is fairly good, you know, plus or minus maybe 0.1. Notice that so the linear approximation is the first Taylor polynomial. The second Taylor polynomial is the green. Again, the function is red. It's pretty good. You see you're having a little bit of a fall off down at the bottom here, but again, you can take a neighborhood from minus 1/2 to maybe 3/2. It's, again, you can accept some error, but how accurate do you need to be? And if I look at the third Taylor polynomial, that's this gold line, it's pretty good. Certainly between minus 1/2 and 1 and 3/2. I mean, well, I don't know. You can see a little error, but how accurate do you want to be? If you want more accuracy, take a smaller neighborhood. Maybe go from 0.9 to 1.1, right? I mean, this is how we use it. I can replace the function by its Taylor approximation if I have enough derivatives, enough smoothness. And again, you see this, right? You see this, the air in the room has all the derivatives. And this is exactly the kind of thing we do. Now, this is a more complicated one because the derivatives are going to get messy. So I wanted to take one where, you know, there was more challenge to this. So why don't you guys pause and try to pound this out so you can check after, say, the first derivative, make sure we're on the same page, the second derivative, and then, you know, we're only taking the second Taylor polynomial because the derivatives are getting messy, so 2 derivatives. Okay, so give it a shot. Okay, so again, it's just good practice taking derivatives. Again, fight smarter, be organized. So here's my function. Again, it's a over b. b is 0, means I'm undefined, so that's where I get the domain. Again, train yourself to think correctly about things, not billions of tricks and gimmicks. Think about the basics, always the basics. Everything's powers, right? X to the first power, x to the first power, 1 is x to the 0 power. So, I mean, everything is set up. So if I'm going to define the derivative again, everything is differentiable as long as I'm not at 1, so I can use the differentiation rules. I'm trying to build my Taylor polynomial around a is 0. So, okay, that's fine. I'm good there. Here's my differential operator. The function f goes in, the function fx comes out. I'm going to substitute in the rule. Again, now if you look at this, what's your choices here for using the rule? Quotient rule, right? Quotient rule. Again, I like the quotient rule in this form. You don't have to. You can do the standard other. It's equivalent. The reason is, later on when we do more complicated problems, I look in the chain rule next lecture, I look at this as modular. If this is a complicated term, right? Notice if you look at all the rules, sum rule, difference rule, product rule, you break it into a chunk of something times the derivative plus a chunk of something times the derivative, right? I mean, that's what they all look like. Something times the derivative of one function, chunk of something, derivative of another function. And the idea, or the reason that this is useful is I'm just going to, if this is a complicated expression, I'm just going to work it out on the side of the page over here on the right. And then when I get the answer, I'll just plug it back in. Same here. If this is a complicated problem, why keep doing it embedded? Why fight harder? Fight smarter. Just take this, work it on the side of the page. When you get the answer, just plug it back in. So you'll see when we do chain rule, you have chain rule and the chain rule, whatever. It doesn't make any difference. We're always going to divide and conquer, right? Take your problem, chunk of something, derivative. Chunk of something, derivative. Break it into two easier problems. If you have to break those problems down, they're separate problems. And again, you'll see a lot of this later on. But again, you don't have to use it. Really, you don't use quotient rule very often. Again, I could break this down on the side of the page here, but it's so basic, right? Difference rule. I don't want to make, I'm not saying everything has to be so hard. Just plug your in. This is the power rule. I'm just simplifying. I want to get a common denominator here. Right, I want to get a common. So this is 1. I get myself a common denominator, add these two terms together, clean it up, and it comes out to be this. This is why cleaning it up helps, right? If you have to take another derivative, I want it to look a little cleaner. So here, just summarizing. My first derivative then is this expression. Again, notice it's still not defined at 1. If the function isn't defined at 1, certainly the derivative is not going to be defined at 1. Right, the derivative is derived from the function. We talked about this before. So here's my rule. Okay, here's my rule. Okay, so if I want the second derivative then, I want the derivative of this. Okay? So try setting that up. I'll start it in a minute and then I'll pause again. But try to set it up and see how far you go. Okay. So my second derivative, here's my first derivative listed. This, right, it's differentiable everywhere, fine, 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 as long as I'm not at 1. So the second derivative is the derivative of the first derivative. And I'm just going to substitute in my rule. And now you're going to use your differentiation rules here. So again, if you haven't tried, give it a shot and see. Okay, let me do this. You don't have to go crazy. What I'm going to do first is there's a minus sign here. And again, this is just why I pick some of this problem. This is good algebra. A minus sign is really a minus 1, right? It's really a minus 1. So I'm just going to take that out, right? Just take it as a constant. It's a minus sign. Instead of, why deal with it? You can leave it in here with the 1 in the top. I just prefer getting it out so I don't have to choke on it later. I know my algebra limits. Now, I'm just going to, again, use the quotient rule on this. And again, you don't have to use this version. Again, it's not my version of it. This exists. People like to personalize this. Oh, I do it. Somebody does it your own way. Everyone has their own style, just as your signature looks different than mine. I prefer this version of it. Okay, it's maybe not as standard in how you've seen it, but it's fine. There's no reason that this isn't valid. Again, notice, and this is why this is good, right? So I have the minus 1 out in front, so I don't have to worry about it. Now notice when I look at this, right, divide and conquer. I have now the calculus is this derivative and this derivative. I'm not going to stress about it. Just pick the easy one, this one, and let's do this one first. Oh, I guess I did this. Fooled myself. I did this. Okay, now I did this on the next page. What I'm suggesting to you is when you're looking at this, fold the paper in half. We're going to do a lot of this with the chain rule. And just this is its own problem. What I'm saying is look at it like a clean sheet. Now, people who've had calculus are going to say, I'm going to chain rule this. You don't have to. Or you're going to just apply the power rule, and that's wrong. What I'm saying is break this off and look at it as its own problem. Look at it with fresh eyes. It's its own problem, right? It's doable. Just look at it. So here I am, and look at it the way we've been doing it. Like I said, fold the paper in half. Do this on the right. You'll see. Hopefully this makes things easy for you. What's my function? That's it, right? That's my function that I'm talking about in this problem, right? This is what I'm looking for. So what do you do step 0? This is why I push this. This is why I push it. I would square it, right? It's only squared. It's just a polynomial. Very simple one. So if I go to take its derivative, big deal, right? It's just a polynomial, right? You can look at the steps, pause and look over it. All I'm doing is it's just 2x minus 2, right? And then I'm factoring out the 2. No drama. Notice if you set up a good technique, This is no stress at all, right? This is no stress at all. You say, well, the exam is so hard or the homework was so hard. Do it right. Train yourself to think about things correctly. Okay? Now, so this is it. It's modular. I'm just going to take this and I'll plug it back directly, right? Now, this is a mistake. I know because in the class people do this all the time and ask. This is wrong. You got the right answer, but you're wrong. It won't work if, for example, this inside was x squared or something like that. Okay, or if it was 2x here or something. Now, look, the power rule means that the function that goes in has to be x to a power. It has to be. You can't make it up. It's not like it's close enough or looks like it. Understand, we're doing math. I'm not asking your opinion, right? It's like playing any game, chess. You cannot make up how the pieces move. These are the rules of the game. The function that's going in here is x to a power. This is not x to a power. This is x minus 1 to a power, right? Again, notice, if you expand out this function, it's x squared minus 2x plus 1. It's all this, all right? My function that goes into differentiation was only x squared. So if you apply the power rule to this, you actually got the right answer, but it's a fluke. It's a fluke. You'll see in the next section in the chain rule that it's just a fluke. If I had had something here like 2x or x squared, you would have gotten the wrong answer. Now, the reason that's a problem is you do it wrong once and you think you know how to do it. And it never works for you again. And then you get frustrated and you think everything's a gimmick or unfair. No, understand. The power rule only works in this case. Okay, it's a fluke. You got the right answer this time and it's never going to work again. Okay, so just be aware of what you're doing. And again, all I did, if you go back, all I did was expand this term into a polynomial in a straightforward manner that I think you'd see if you looked at it as a clean sheet, right? Good technique, like I said, try to develop good technique and you'll see. So back to where we left off, I just plug this right back in. And again, my idea, fold the page in half and work this problem as its own problem on the right side. And we're going to do a lot of this. Let me be clear. When we do the chain rule in the next section and so forth and so on, this is common. Okay, the problems get longer, but they hopefully aren't harder for you. Work this out on the side and just plug it directly in. Now, of course, I should have done, maybe I should have done this one first. It's easier. I know the derivative of 1 is 0. It's a constant. I get that, but I just want to emphasize there are rules here. So 0 times this whole chunk is 0. And then I just have to clean up this whole back end here, right? Just clean this whole back end up, right? That's all I'm doing. I want to start a new sheet of paper here. So I'm just cleaning up the back end, again, however you want to do it. I'm just putting in the various steps and emphasizing the algebra in these steps. So if you want to look at it, pause and go through it. Again, I don't run from the algebra, right? Certain algebra things come up over and over again, and that's why I'm including it here, right, in these steps. So try to practice, try to use the rules, and you'll get more comfortable with it as the semester goes forward, right? And so, that's what I have. So that's my second derivative, okay? And again, a lot of it was just algebra, and I know it can be frustrating. So keep practicing, and you'll get better with it. It's usually the same rules. Like I said, I listed all of them. I only had 20-some for the whole semester, so. Now, determine a second polynomial. Taylor, trying it. We just did this in the previous problem. Make a table, and then plug into the formula. Again, I'll pause, and I'm going to put it up here now. So here's my data, right? I just make the table. There's my function fx, the second derivative. And notice everything's, a is 0 here, so I'm plugging everything in when a is 0, right? So 0, minus 1, and minus 2, that's the function value, the value of the derivative, the value of the second derivative. Okay? And I'm just going to plug it directly into the formula. All right? Once more, I'm building everything around x equals 0, so a is 0. So everywhere a is 0, so it's x minus 0. And all the functions are evaluated at 0. The Taylor polynomial approximates the function. I just substitute in f of 0 is 0, plug that in. The derivative at 0 is minus 1, right? Just plug that in. The second derivative is 0 is minus 2. And now it's just a matter of cleaning it all up. And look how simple this is. Notice the original function is, well, not so simple. So again, it's so easy. If you want to, again, we haven't done integration, but integrate it. You'll do this next semester. It's just easy. Look at the picture. So the function is this red line. And again, the linear approximation is not bad as long as you have a limited neighborhood. You can zoom in, but it's not bad. But look, the second, and this is only the second derivative, right? If we took the third derivative, it would be better. Notice we're capturing some of the shape here. It still gets bad over here, and it's not good. But again, it does have a better neighborhood of approximation than the linear approximation, right? I mean, between maybe minus 0.1 and 0.1, it's not too bad, right? It's not too bad. And again, if I wanted it to be better, I'd take the third Taylor polynomial, the fourth Taylor polynomial, the fifth Taylor polynomial. Again, they're polynomials, and you can just do it very easy using the derivative calculator. Okay, so again, I want to emphasize here, this is the last one we're going to do here. It's really just taking higher order derivatives. But again, what we're really interested in this approximation, if you have those derivatives available, and those derivatives being smoothness. So if you have this smoothness at this point, right, the derivatives available, you can represent the function as the linear approximation, okay? I mean, you'll see how we actually use this later on when we look at implicit differentiation. You don't even know what the function is. You can't write it out explicitly, but you could represent it as a Taylor approximation, right? Is that how accurate as you like? So this is important, and it does have uses. So keep this in mind. This Taylor series stuff is going to come up all through the course, okay? Okay, good luck with that then.